Hello from the Forstronics YouTube channel. Welcome to tutorial on digital to analog converters or DACs and an example using Microchip's MCP4728. And this is part 2 in a series of 2. Before I get started, I'll mention check out forstronics.com for our design services, as well as we have some low-cost Arduino Uno and Maker 1000 boards. They're not low-cost, they're just on sale, I should say. If you like what you see here, please subscribe to my YouTube channel and hit the thumbs up on the video. And you can see I have the symbol for my favorite PCB manufacturer, PCBWay. I'm going to show you, I made an example board with the DAC on it for this video. And there's an easy way for you to go to PCBWay and purchase that board if you want to. It doesn't have the parts on it, it's just the board, so you still have to build it up. But they have a great way to now share projects, so I'll show that as well. All right, let's get started. In part 1, we discussed what a DAC is. We talked about some example applications and some example specs, namely resolution, accuracy, and speed. We then showed some examples related to accuracy, and then in part 2 we're really digging into an example DAC, the MCP4728, which is a 4-channel DAC from Microchip. So the whole point here is to kind of show how to use it if you ever needed a DAC, and also just to kind of show some of its features and what to expect in a modern DAC IC. And then also I'll have some Arduino code for controlling the DAC. I used a library found on GitHub, and I'll provide information for accessing all that. Okay, here I'm just showing a screenshot of PCB's front page website. This is where I buy my PCBs. They're great. They have great prices. And even though, I'm in the US, they're way off in China, their turnaround time is excellent for getting the boards done and sent out. So I always use them, and what I was talking about, and I'll provide a link to this, is now they have this shared projects. I'm not sure how long they had it, but this is the first time I've noticed where, for hobbyists and makers and open source, you can now share your projects, and it doesn't cost you any extra to buy them from them. Okay, here is the slide I left off on part 1, and we just went over some of the features in the MCP4728 architecture. And the whole idea here, one of the things I point out is modern DAC ICs have a lot of features built in, because really this is the block that makes up the DAC, right? The 4 different DACs. And it has a lot of other features. Most of them I talked about already, but I2C communication for setting up the DAC. You can access saved values from EEPROM, so when the DAC powers up, it goes to whatever value you have stored, so you can set a default for when it powers up. The LDAC pin allows you to synchronize the outputs, and I'll actually show an example of that. You can control what voltage reference to use, you have buffer amps, so on and so forth. So let's see some of these features in action. So we're going to look at 2 tests. First, we're going to look at a speed test, and I think I misspoke in part 1. So the MCP4728, I think in part 1 I said it does about 150,000 samples per second at its fastest speed. I'm not sure where I got that from. I looked at the data sheet again and I did not see that. And so really the output speed is dependent on the clock rate of the I2C signal. And your controller, in this case I'll use Arduino, is the one that sets that clock rate. Now for I2C, the fastest clock rate you can do is 3.4 megahertz. Unfortunately, Arduino has a setting for setting the clock rate speed, and they call out 3.4 megahertz, but I don't know which Arduino can handle that. So I tried it on the Arduino Zero, and that one did not work. So if anybody knows which Arduinos support that fast clock rate, let me know. I was only able to do a 400,000 hertz or 4K hertz clock frequency using the Uno or the Zero, and so that's what we'll have to look at. So we won't be able to see the chip goes as fast as it can. We can just see what it can go at 400 kilohertz clock rate. There's other specs that limit its output speed, but it's mainly the I2C clock rate. And I believe from the data sheet it supports 100K, 400K, 1.7 meg, and 3.4 meg. Then we'll look at an output sync test using the LDAC pin. And that's useful because I2C can only feed in data to the 4 channels serially, so it can't feed them all in at the same time. The LDAC pin, though, allows you to output these samples synchronously if the channels have to go in a certain order. And I actually probably will not show that in action just for the sake. I have a lot of stuff to cover in this video, but I'll show a picture of it and we'll see the code for it. So let's look at the speed test. So before I show the video of the speed test, and this is one of the reasons my videos have too much content, is I decided last minute to add a filter to the output and kind of show you how a lot of DACs are used. As I mentioned before in part 1, the MCP4728 is not a DAC known for its high speed, and higher speed DACs, when you get into the hundreds of megasamples per second or even gigasamples per second, are tough to use for a hobbyist because they require some tight engineering. But even for lower frequency DACs, you often need to know how fast they can go. So that's what we'll look at. But what I added here is a low pass filter, because for this example, I create a sine wave, but when you see a DAC output, it's really like a step sine wave. So we use this low pass filter to filter out that step and give it more of a smooth sine wave look. And we'll see this in the example, because in the example, I use an oscilloscope to measure the output of the DAC and then the output of the filter. And with my filter, and I have a video on low pass filters, so I would encourage you to check that out. But my low pass filter is really just this resistor and capacitor, and I chose a frequency roll off that is, a little farther out than the output frequency of the DAC, and we'll see that in a second. And the idea is these buffer amps, this low pass filter would load down the output of the DAC, so you'd see a reduced amplitude. So I use this buffer amp or op amp to basically create a high impedance input and a low impedance output. So I maintain my amplitude without filtering it out and losing some of the power of the signal. And then I just have another buffer amp for the load. This I decided to do last minute, so you'll actually see the DAC on a PCB board, but you'll see this on a breadboard because I just grabbed the op amps that I had available and a resistor and a capacitor. So anyway, just wanted to show that. Let's take a look at the video for the speed test. All right, let me pause the video right here. Here we're looking at the DAC board I made, which you'll be able to get from PCBWay if you want. And this is the actual MCP4728. And here's a 5-volt regulator to feed the power supply for the DAC. And then here's an op amp I just threw on there, precision rail-to-rail op amp. So what I did is I connected channel 3 and channel 4 to the op amp, and the op amp has a gain of ×2 using these resistors. So you'll actually see if you use this board, channel 3 and channel 4, the output amplitude is doubled by this op amp. Now I don't use this op amp in this first example, but it is used in the second example. What else did I want to mention? Oh, this board has a VCC input. So just to note, VCC is fed to the regulator, which creates the 5 volts, but it also serves as the power supply for the op amp. And I'm not going to go into op amp theory. There's plenty of tutorials out there on op amps if you're not familiar with them. But, the op amp output is going to be limited by its power supply voltage. You can see I have this hooked up to an Arduino Uno, which is controlling it, and the code's running there. Here is my filter and buffer amp setup. Let me try to get a more clearer picture right there. You can see my 2 op amps. Once again, these are just what I had in lab stock. These are actually pretty low cost op amps. You can see the capacitor and the resistor, and then I have a power supply that has positive voltage and negative voltage, so I can get the full range of the op amp. And this is essentially VCC for the DAC board. And so if we press play, I show my dual power supply for this, and then we take a look at the output from the DAC and from the filter. So on the top, this is the output from the DAC. So basically what happens is it outputs a value, and there's 24 different steps. So each sine wave is made up of 24 points. I could have chose less, I could have chose more. The less points I do, the faster I can do the whole signal though. But basically each step represents the dwell time. So I set it to this value, then I2C has to communicate and set it to the next value. So that's why it has that stepped look. But then when we put it through the filter, we get a much smoother sine wave, right? And it's hard to see the frequency value, but it's about a 137 hertz. So if you do the math, 137 hertz with 24 points, that's a dwell time of about 300 microseconds per point. And that's using the I2C 400 kilohertz clock. Once again, if we did 3.4 meg, which I wasn't able to test, we'd get a much better, higher frequency. I'm not going to go into filter theory, but the whole idea is these steps have higher frequency components, and that's what the filter is taking out. But the filter's frequency cutoff is lower than is higher than 137 hertz. That's why we get the clear sine wave out. And if I didn't have the buffer amp, this output would be a lower amplitude. And the reason I decided to put this here is if you've ever used a waveform generator or a function generator and you have one in your lab stock, this is what they do, right? They have a DAC creating the output signal, and then they'll have a filter which gives the signal a much smoother look. And a lot of them will have different types of filters to choose from, or you can even look at the raw output. But anyway, that's how a lot of waveform generators work. Yeah, let's take a look at the code from the video, and I'll also show the code for test 2 before we see test 2. Okay, here is my Arduino code. One thing I want to call out right away is I got this library, the MCP4728.h from GitHub. Adafruit actually has a MCP4721 library because they have the one-channel version of this DAC and they sell a board for that. But this person made the MCP4728.h, and I'll provide a link. And I thank that person. I'm too bad I don't have their GitHub name right in front of me. But anyway, thank you to that person for making that. I'll run through the code kind of quick just because this is going to be a longer video. But we create our object using the library MCP4728. DAC is our object. Then these variables are related to the sine wave signal. So 24 points, I create an array. I need pi times 2 for creating my sine wave. I then also have the clock frequency for the I2C communication signal. Then I have test 1 and test 2, and basically tying these digital pins to high or low chooses what test we're going to do. T1 was the speed test, T2 is the sync test. And then for test 2, I need to control the LDAC pin, so I set a pin for that. In the setup, I create the sine wave, and the reason I do that is because for the speed test, I don't want to calculate the sine wave as I'm outputting it because I want it to be as fast as possible. So I just do a for loop based on the 24 points. I do my calculations, I have my sine. One thing to note is each bit is actually an offset based on the 12-bit DAC. And the whole idea here is the DAC can't do negative voltage. And so what we have to do is we have to make sure the sine wave is not a negative output, because that's what will happen if you use the sine function. I set up my pins for test 1, test 2, and LDAC. I begin my wire library, which is what Arduino calls I2C. I set my clock frequency. Unfortunately, 3.4 megahertz didn't work. Unfortunately, too, this function doesn't return whether that speed is valid or not for the Arduino you're using, which is kind of annoying. Then I start setting up my DAC, and I showed, I think, some examples of this in part 1, but I attach the wire library object. I do some reads on the current settings, but I don't actually use them. I set my references, which I just use VDD. I set the power down mode to normal because I'm not concerned about saving power. And then I also set the op-amp gains to just 1. Now, with my example board, I have another op-amp on there, so you could actually do a gain here and do a gain on the external op-amp. All right, I don't use the DAC enable true because I'm controlling the LDAC pin independently, and that's all that the enable does. I then do test 1, and like I said, based on if you have the digital pin 3, I think it is, tied to low, or if you have 4 tied to low, determines what test you do. So for test 1, which we just saw, I just do a never-ending for loop where I just run through the samples and then output them as fast as possible. And you can see we got about 137 hertz, and each dwell time of each point was about 300 microseconds. Then the second test, which we didn't see yet, once again, never-ending for loop. I go through, I should mention, I do a sine wave for each one. And what I do for this is each one, I shift the sine waves, the phase of a sine wave, about 90 degrees. So each sine wave is a quarter difference in time, if that makes sense. And then the way I can make sure I do that is I do a little math each time, but I don't output the points until I do this digital write LDAC low, and then back up at the top of the loop, I write it high. So that way the outputs stay synchronized, which is important for certain applications. All right, what should we do next? Let me show the schematic and show where you can get the shared project, and then we'll look at the output for test 2. So here you're looking at the schematic in Eagle, which is a software tool for generating PCBs. So we're just looking at the schematic. Here is the MCP4728 chip. For I2C, you have to do pull-ups on the clock and the data port. So SCL is the clock, SDA is the data, and then the LDAC chip I pull to high as well, and we use the Arduino to pull it low. And then of course I want my 5-volt signal to be as clean as possible, so I have a filter cap there. This is my regulator, the LP2985 from TI. And then here is my op amp, TSB712 AIST. And this is from ST Micro. It's a precision rail-to-rail op amp. That's why I chose it. It's a little pricey, but for this application, who cares? But the idea here is it's a rail-to-rail, which means that you don't need a negative voltage to get close to zero. And once again, I'm not going to go deep into op amp theory, but for the lower cost op amps that I showed for the filter example, I needed a negative power supply. This one I don't. And basically, the gain is set to 2. And you can see I have DAC 3 and DAC 4 going in, and then I'd have DAC 4 times 2 coming out. And then I have a pin header where I have VCC. Remember, VCC goes to the regulator and it also goes to the op amp. Then I have my clock pins or my communication pins from the Arduino. I have my LDAC pin, and then I have the output for each one of the DAC channels. DAC 1, DAC 2, and then DAC 3 and DAC 4 go through the op amp, and they're amplified. And then I just have another smaller pin header if you want to access, the 5 volts, the VCC again, or ground. All right, and if you remember from the video, here's a picture of my board, and I'm looking at this from the PCB Way Shared Projects website. Once again, I'll have a link to this. But the idea is you can see the board. Remember, you're just buying the board. You still have to build it up yourself, but I'll have information on the BOM, the parts, things like that. And if you want to buy it, you can, and it has links and information about the board. But I thought this was a really cool feature from PCB Way, and I plan to use it for future projects, so anybody who wants can get this PCB. The way I do my PCBs, by the way, for sample or prototypes, is I build them up by hand. So I use solder paste, I put on the components, and then I bake them in a toaster oven, which is my reflow oven. And I think I have videos on that too if you want to check it out. It's something you got to have a steady hand to do. All right, and finally, I wanted to show the final test output. So if you remember that same oscilloscope I showed in the video, you're looking at a screen capture. They changed the background to white so you can see it better. But here's 3 channels. Now, I only had 3 oscilloscope probes. Otherwise, I would show all 4 channels. So that's why we're only seeing 3. But remember, in this one, we're changing the output for each channel and then using the LDAC pin to output it. Now, notice our frequency slowed down, right? Because we can't move as fast when we do it this way. So we did lose some frequency, but you can see, once again, these are not filtered, so you can see the stepped output. Here's channel 1. You can see channel 2 starts 90 degrees, approximately 90 degrees later, and channel 3 starts approximately 90 degrees after that, and then if we saw channel 4, it would start somewhere around here. So this is just using the LDAC pin to sync the outputs. One thing I want you to notice, though, is 5 volts per division, per vertical division. You can notice channel 1 and channel 2 are only 5 volts, because that's the power output of the voltage value of the VDD fed to the DAC. But since channel 3 is going through the amplifier, it gets doubled. So that's why it's 10 volts. So that's why it's higher than the other 2 channels. Also notice it's not quite a quarter out of phase from channel 2, and the reason is probably the op amp is affecting the phase a little bit. But anyway, it's not a big deal for example purposes. All right, that's it for part 2. Thank you for watching. I appreciate it. And I'll provide links to the shared project. You could access it at PCB Way. I'll provide the code somewhere. I don't know yet, probably on my blog. and then also provide a link to the GitHub library. If you have anything to add, anything you think I missed, or anything important, use the comment section. If you have questions related to this video, use the comment section below. Thanks again for watching.